17% into tin plate, and this 13% is going to be getting bigger and bigger all the time, goes into chemicals. There are of course brass and bronze, others float glass, etc. Let me talk then now about some of these assured markets for certain areas like solders, tin plate, and so on. Just want to intimate you with the market sustainability and technology trends. Now, this is a very, very secure position. Solders, lead-free solders contain 82% tin. And plumbing solders and household electronics, well established, no one can take that away. But when you say lead-free, what else? How does a solder look like? Actually, it's a tin, silver, copper alloy. The price factor is the issue. Silver is costly. So now they have produced a new generation of alloys with less silver content, very effective as well. And the buzzword now in the solder industry is nano solders. That's also coming into vogue. And the current solders, lead-free solders, are finding a new application in automotive and medical device sectors, and is project like a second wave, as it were, and is equating to 17,500 tons per annum. So the prospects are very good for solders. Tin plate. What is tin plate? Tin plate is nothing more than a thin coating of tin on steel to prevent the steel from corroding. An excellent packaging material is a green packaging material. Why do I say green? Let's look at some of the advantages. Tin, of course, tin plate, attractive surface finish, excellent corrosion resistance, workability, solderability, paintability, printability, you name it, you can do anything with the tin plate. And then easily extracted from domestic refuse magnetically and then recycled back. So on sustainability grounds, tin is that. And it has withheld challenges from other Tetra Pak and plastic alternatives, which always are not free from environmental issues. So now in developing countries, this is the packaging material of choice. India has no tin. China has plenty of tin. You need to look at possibilities across our borders. Pewter and other tin-based alloys. Now, tin alloys have been known to human beings for thousands of years. In fact, bronze has been known since 3000 BC, and bronze contains 12% tin. There are new frontiers, and that is excitement. This alloy of tin with niobium is a type 2 superconductor, which is used in superconductors in superconducting magnets. I'll talk about this. Its nearest competitor, the one that's going to give it a run for its money, is niobium tin. But it has advantages of niobium tin because it has a higher, at its critical temperature of 18 K, it has 24.5, that's a magnetic field, higher magnetic field than niobium tin alloy, which has only 8 Tesla. Nowadays you have the, maybe I can go to the next slide to show you that you see in MRI, for example, magnetic resonance imaging, you use superconductors and you need these coils. So niobium coil windings on the magnets, electromagnets there. So the problem originally was they were too brittle. Now there's a special technique has been developed so that to draw them is cold drawing. So this allows a window of opportunity, and now tin niobium standard materials is set to conquer the market here. And you can see that the MRI, they use 4 Tesla, 9, 15 Tesla. So you need material like niobium tin. Let's go back here. One controversial application, still we are not sure how it works, but some will swear it works, and that is the use of tin alloy-based fuel-saving devices as porous metal pellets. Now this is a stainless steel high-pressure chamber. You have neodymium magnets at either end, and in between you have tin pellets, and then you have rotating blades there, which break up the tin pellets. And small, minute, microscopic particles of tin that go into the fuel somehow influence the combustion characteristics of the fuel. and you end up saving fuel. There's one, as a scientist, I will not accept the argument there that the magnetic field somehow breaks up the long chain hydrocarbons into smaller chains. But there is a potential here, but there's a market as well. Tin chemicals. Now this is an area of great interest to all of us, to me in particular, and to my workers, fellow colleagues, students. We have worked on this for many years now. Just as a background, what are tin chemicals? Tin is a metal, and it has exists as you find it in the earth, underground, or it exists as cassiterite, which is tin oxide. So tin oxide, combined with oxygen, is already a chemical. It's already a metal. A metal converted into chemical. You could extract the tin from the tin oxide. So there, the tin exists in what is called a valence state 4. The chemists in the audience will know this. And also has a stable valence state of 2. And there are a lot of inorganic tin compounds which are non-toxic to mammalian aquatic life. What we were interested in when we were doing research in a very big way at the University of Malaya was that we focus our attention on those chemicals of tin which contain tin carbon bonds. The word R is a symbol for an organic group, carbon containing group. There is a tin carbon bond. You have different types. There are 4 ligands or 4 groups you can attach to tin. I try to be as non-technical as possible. You can have 3 organic groups, 2 organic groups attached to tin, 1 organic group. The biological properties are mostly associated with tin compounds with 3 organic groups, whereas these are function as catalysts and all that. And commonly you'll find the R group is a butyl group, which means there's 4 carbon atoms. There are some groups which contain 8, but that compound, which is trioctyl tin, is totally non-toxic. I can swallow it and still come back and give another lecture, but not with the other ones. If you use triethyl, probably by the time it enters, the moment it enters my gut, I'll fall dead. So the choice, what you choose, what sort of R groups you put on tin is very critical. But what we want for low mammalian toxicity basically is butyl and phenyl. And anyway, the total, the inorganic tins and the organotins combined, 150,000 tons annually, and the market is growing. But the excitement, let me tell you a little bit more before I talk about the applications. There'll be more pictures. It'll be much easier for you to follow. Some inorganic tin compounds. Here is tin stannous chloride. Is a plating chemical electrolyte. We get plenty of huge market for this one. Tin fluoride is used in toothpaste. Tin octanoate is used as a catalyst. I'll talk about that later, as a dry and additive. So many applications. You can look, when you look at this, you look at the industries that are connected with it. Polyurethane foam, silicone rubber, paint industry, coatings, inks. You know how the tin is filtering into all these. Stannic chloride, there's a tin in the valence state 4, is a catalyst for homogeneous alkalization. Alkylation of, you know that, as chemists will know cyclization. Stabilizer for perfumes and color. And then, this is quite interesting. You can use tannic chloride, put a coating of tin oxide on float glass. That will strengthen the glass. You can't break it. I will focus on one, tin oxide. Chemists will like this rutile structure of tin, 6-coordinated tin, oxygen is dry. Now these are the applications. Thin glazing of ceramic materials, giving them a white, opaque and glossy glaze. Polish for marble granite. So if there's any guys in the audience who are interested in the marble or granite business, this is the tin glazing, tin oxide can be used. Now the beauty of this is it's an N-type semiconductor with a band gap of 2.7 to 4.2, outstanding electrical, optical, electrochemical properties. China's market is huge. China's electronics market is expanding so much. There's a great demand for this. transparent conductive tin oxides. You can use tin oxide fluorine doped in the production of low emissivity glass. The indium tin oxide for liquid displays, flat panel displays, touch panels, aircraft windscreens for de-icing, solar cells. Next two slides will elaborate on this. It's an essential component of solid-state gas sensors. We can detect carbon monoxide and other hazardous gases. And this sort of tin oxide gas and solid-state gas sensors have competition. For those in the biomedical field, the last sentence here, glucose oxidase immobilized nano-tin oxide tinplates are receiving interest. But when you put the glucose oxidase, you immobilize it onto nano-tin oxide. So you can detect levels of glucose. So again, across a range. I was talking about low emissivity glass. Basically, you are applying the tin oxide as a very thin coating on the glass. This is IR reflecting. It reflects IR rays. It reflects heat rays. What does that mean? That means to convert the glass surface from a heat absorbing high emissivity to a heat reflecting low emissivity material. And if you can have this here, you can keep the sun out during summer. You can keep the heat in during winter. In the area of solar cells, I've given two examples here. Cadmium telluride solar cell. The light comes straight through the top glass surface through this low resistivity transparent indium tin oxide layer onto the PN junction here. The cadmium telluride is a P and then this is the N. So electricity generated. The ITO layer facilitates movement of current across the top of the cell, and you have a metallic back, which is normally gold or some aluminum alloy. Now, this interest in cadmium telluride solar cells, there's a lot of research now on alternative energy, and sunlight, solar energy is being looked at, and people are trying to make solar cells very, very cheaply. The advantage with cadmium telluride solar cells is that the band gap perfectly matches the distribution of photons in the solar spectrum, and the efficiency is about 15%. Now this one, the standard, the gold standard now is of course the silicon crystal wafer. They have tried to make thin films of silicon, amorphous silicon, but the problem has always been that the light conversion efficiency is low. But researchers at they have put aluminum nanoparticles on top of that ITO, and these absorb and scatter the light, so the light stays on the surface, and apparently the theory is that the total absorption increases. In the use of tin oxide for gas sensing, this is how they look like. The gas sensing is due to surface band bending induced by all these ionic molecules adsorbed onto the tin oxide. Before I leave the inorganic tins, two applications, two compounds need to be mentioned. Zinc